One feature that Desmos provides to its content creators that I really want to highlight in this video is the slide feature for variables that exist in an equation or in a function or in an expression. Right now what I have is a graph that I've created that has displayed a few of the major functions that you would cover in an algebra curriculum. And what I've done is I've generalized these functions so that I don't really know what the value is that's in front of the function. I don't really know what the value is that's in front of any of these. But there are a lot of different things that I could do to change these functions by adding these variables a, b, c, and d, and I've placed them in the same spot in each function so that I'll be able to change those variables and see how the functions behave. And I'll just show you what I mean by that. So this parabola here, right now, is the function 1, because a is 1, times 1x, because b is 1, plus 0, squared plus 0, because d is also 0. So I've set all my sliders to these specific values. This is just my basic quadratic parent function, y equals x squared. All right? But what I can do is I can change different parts of this quadratic. And let's say that all I want to do is change d, and I want to see what effect changing d is going to have on this function. I can go down here to my slider, and instead of just typing in different values for d, I can slide d up and see what the function does when I increase that number d. So when d goes up to 7, it looks like my function shifts vertically by 7 units. And if I decrease d by 7, I should see now that the function decreases by 7 units. So what I'm going to do is I'm going to set d back to 0, and I'm going to change one of these other variables. It looks like the c that's inside the parentheses there might be an important thing to look at. So based on what I just observed with d, I might present to my class that, well, c maybe should do something similar, and they would probably say that, well, instead of going up and down, maybe c moves it left to right, and when I increase c, it looks like the function should probably go to the right, and when I decrease it, it should go to the left. And what they're going to see is that by playing with the slider, it in fact does the opposite of what they thought it would do. When I move c to the right, the function travels to the left. And when I move c to the left, the function travels to the right. So that's an important observation that we're going to make as a class. I can also show them how increasing a makes this parabola narrow quite a bit, or how decreasing it makes it widen. And then if I were to make a be negative, we would see that reflection over the x-axis that we've talked about that comes from making the entire function negative. So the slider feature is a really useful one because they'll be able to see then how that applies to all the other functions that we talk about. I could just turn them all on just to get a really busy but useful graph here and see, does changing d affect all these functions in the same way? And it looks like as I increase d in all of these functions, whether it's trigonometric or if it's an absolute value function or whatever it is, increasing d brings my function up. Decreasing d brings my function down, and it doesn't even matter what type of function we have. We see that same relationship there. We should see the same thing with c. As I increase c, it goes to the left. As I decrease c, it goes to the right. And that's going to help us build connections and get a lot better with interpreting functions just based on the equations that are given. Currently in my class, we're using the trigonometric functions quite a bit. So we've been playing around with what happens when a increases and attributing that to the vocabulary word amplitude. As I increase a, we're going to say not just that the function gets a little taller or gets a little shorter, we're going to say that the amplitude increases, and if I make it negative, again, we do see that reflection over the x-axis. So playing around with this slider feature is a really good way to visualize what's happening to a function when you change a particular element of it. Once students have seen this behavior and have access to this slider graph, I will usually give some sort of an activity, something that allows them to explore a little deeper and maybe make some connections between one type of function and another type of function or connected to the real world. So in this case, I assigned this activity, which allows students to explore a little bit deeper into the relationship between sine and cosine. So there are some other things in here like card sorts and sketches and things like that that students are asked to do on their own. But one way that I've integrated the slider tool into this activity is I've given a general graph of a cosine function and have given a very specific graph of a sine function. And so what I would want to do here is ask the student, well, how can I map f of x, this cosine function that's here, onto the function g of x, the sine function that's here, and get them to see the relationship between these two things. So they'll play around with the sliders, and hopefully they'll come to the conclusion that I should make d 1 because my sine function is also a d value of 1, and they'll play around with the sliders and realize that it looks like the sine function has a 2 in front of it, so I should maybe make my amplitude 2 of the cosine function. So now f of x has that amplitude. And now that everything is the same, we see that there is a little bit of a difference between these two functions. And the difference really is just kind of the y-intercept. But if I were to find a way to move the cosine function one way or another, I should be able to get it on top of that sine function. So this is where their knowledge of manipulating that c variable will come into play. And I have set here that I want the step to be in radians. I want it to step up by pi over 2 and step down by pi over 2 when they slide it, so that they're not just getting whole number values, they're actually getting these radian measures, which is what we would plug into a trigonometric function anyway. And I've set the boundaries for the domain of this function to be from negative 2 pi to 2 pi. So what I can do as a student is I can just press play here and watch this function move and try to figure out when it is that these functions are the same. And I should see this happen a couple different times while this thing is playing out. So I see that as my c value decreases, my function's moving to the right just like I thought it would. And as my c value increases, my function moves to the left just like I thought it would. And I'm going to pause it here when I think I've found a c value that maps one function right onto the other. So a c value of negative 1.5707, we're not going to write all those down because we know that what this really is negative pi over 2, looks like a c value that I could use to map my cosine function onto my sine function. So from this conclusion, I would be able to state that if I replace that a with a 2, and if I replace that c with a negative pi over 2, and if I replace that d with a 1, I'll be able to make that cosine function be exactly the same as that sine function, and the rest of the activity builds on that. So that's my perspective on why the slide feature can be so useful as a teacher, especially in an algebra classroom. It's by no means the only way to use that feature, and I would love to see some other interesting and creative ways that features like this one have been used. But hopefully it's been informative, and I'm looking forward to hopefully learning more about the Desmos graphing calculator and its activities as well.